Alright, continuing where we left off. So, in order to do double displacement to predict whether or not they will react, we need to see if there's a precipitate. We need to use our solubility rules to see if we'll end up with a solid on one side. Because we know there's a precipitate, we know that this reaction will occur, it being double displacement. We can also write something known as the net ionic equation. So in this previous equation, we see that lead nitrate and potassium iodide are mixing together. Since we're putting them in water, dissolving them in water, they form ions. When we mix them together, we see that the ions are going to basically make a solid, lead iodide. This leaves us with potassium and nitrate ions still remaining in the container. These ions are called spectator ions and do not contribute to the overall reaction. This is important because usually we can make a lot of substitutions. Usually whenever we're doing ionic reactions, all we care about is getting two ions to react together. Here in this equation, we're getting lead ions, lead 2, to react with iodine ions to make lead 2 iodide. So we have the equation, the overall equation that's balanced. Lead to nitrate mixed with potassium iodide gives us lead 2 iodide, which is a solid, plus potassium nitrate. There are two ways of doing this to convert this into net ionic. One way is to recognize that we have a solid here, and only the ions that form the solid will make the equation. So we know that we're going to get from here, or lead 2 plus, and from here we get our iodine negative. So the net ionic equation would be lead 2 plus, and this would be aqueous, is still dissolved, plus iodine, which is aqueous, gives us lead 2, which is solid. To balance this out, we know we need 2 iodine on the right. We have 2 iodine on the right. We need 2 on the left. So this would be the net ionic equation. And this is mostly the most easiest way of doing it. We know that this is going to be our solid. These are the only ions that contribute to it. Another way is to just break this whole equation up into ions. And then eliminate the ones that appear on both sides. So this this doesn't form ions because it's a solid. So we have potassium and potassium, nitrate and nitrate, and the only thing left is lead 2 plus and iodide, giving you lead 2. This is solid. That's aqueous. That's aqueous. And we need 2 iodine on the left to balance 2 iodine on the right. So let's do another example. So write the balanced equation, balanced chemical equation. For sodium carbonate and calcium chloride. So what's the equation for sodium carbonate? So carbonate is CO3. What's its charge? And sodium is Na+. So when we combine these together, how do we combine them? So it'd be Na2. We need 2 sodiums to counteract this 2 charge. Plus. And then calcium chloride. Calcium has what charge? And chlorine has -1. So we need 2 chlorine. What type of reaction is this going to be? We have 2 ions here, 2 ions here. This would be double displacement. We have Na and Ca, and we're going to change out the anions. So chlorine is going to come over here, and carbonate is going to come over here. Are these 2 balanced? So what should be their correct formulas? What I meant by balanced, are these the correct compound formulas? So when we change these out, remember we have to balance the charges. So Na is plus, chlorine is negative. Those charges cancel each other out. It's 1 to 1. And calcium is 2 plus, carbonate is 2 negative, so it's a 1 to 1 ratio. So these are the correct compounds. Next, we need to see if this is possible. Does table salt, NaCl, dissolve in water? What rule is it, by the way? You should know table salt dissolves in water. All chlorides are soluble unless mixed with silver, lead, or mercury. That is sodium. It's not silver, lead, or mercury, so that means chloride is soluble. Likewise, this chloride is soluble. And this is a carbonate. Number 3 tells us all carbonates are insoluble. So this is insoluble unless it contains rule number 2 cations and magnesium, calcium. So it says rule number 2, which includes, so looking at it, this tells us, so all carbonates are insoluble except with the cations in rule 2, and rule 2 contains sodium. So this is the exception. So it's going to be the opposite of insoluble, making it soluble. So this will be aqueous. What about this one? Calcium carbonate. Is it soluble or insoluble? So rule 3 says all carbonates are insoluble. Calcium carbonate solubility. The PowerPoint says it's insoluble, but our rules state that this should be soluble. So I think it's the PowerPoint. What is y'all's paper?
Got the same rule, but it doesn't have the add-on. Like it said are insoluble except with add-on and rule 2, but it doesn't have the.
Yeah, so y'all's paper is right. The PowerPoint is wrong. I don't know why they added this. So this thing in yellow is wrong. Y'all's paper is correct. This is insoluble, so we make it solid. And I just Googled it. It is practically insoluble in water. So note the PowerPoint is wrong. So we have 2 chlorines and 2 sodiums. So to balance this, we just double this. And that's it. 2 sodium, 2 sodium. 1 carbonate, 1 carbonate. 1 calcium, 1 calcium. 2 chlorine, 2 chlorine. And that's balanced. So our overall balanced chemical equation is Na2CO3 CaCl2 2NaCl So that's our balanced chemical equation. What would be the net ionic equation? So the only solid we have on the right-hand side is calcium carbonate. And what ions were used to make it? Calcium ions and carbonate ions. That's balance. We just need 1 calcium ion with 1 carbonate ion to make calcium carbonate. Does that make sense? What are the spectators? So spectator ions. It's any ion that isn't in the net ionic. So that'd be sodium plus. That would be chlorine negative. And that's it. These two ions are not used in the reaction. Why is the net ionic equation really useful? Let's say that you want to make some calcium carbonate. So you know the balanced chemical equation. Sodium carbonate with calcium chloride gives you salt, which will dissolve in water, and calcium carbonate. What would happen if you look inside your drawer and you have no calcium carbonate? What would happen if you change it to magnesium carbonate? It wouldn't change anything. You can replace this chemical with magnesium carbonate, assuming magnesium carbonate dissolves in water. It still needs to be aqueous. So let me look up soluble, insoluble. Yeah, it's insoluble, so that doesn't work. What's another carbonate that's soluble? Let's do potassium. It's soluble. So let's say that you had instead potassium carbonate in your drawer. It dissolves in water. It is aqueous. That means you can replace your sodium carbonate with potassium carbonate and make this chemical. And we know that all we need, the only thing that changes is we just need one ion to one ion. So as long as this is one ion of that, then it doesn't change. The only thing is mass. Which one weighs more? The thing with calcium versus the thing with sodium. So we'll need a different amount of grams of potassium carbonate to make it work. So you just change the ratio of how many grams you use. But basically that's it. So writing a net overall simplifies it down to where you're only concerning yourself with the ions. So we see there's the solution they provided. Remove the spectator ions, those that are soluble. Basically, you remove all the aqueous on the right-hand side, and if they match on the left-hand side, you remove them. And that's a result. Everyone think they're comfortable with the net ionic? Everyone think they're good at balancing equations? So, let's look at redox reactions. Electron transfer reactions are called oxidation reduction. Or reduction oxidation. Usually we simplify the two words to redox. It occurs when the oxidation numbers change. Results in the generation of electrical current. And therefore this field of chemistry is often called electrochemistry. This would be the reactions that go on inside a battery. I don't think it has to necessarily create electricity always. Because I know of some redox reactions that don't. At least I'm pretty sure. But I've never thought about them as producing electricity. At least. is basically the oxidation number. And remember, you can think of oxidation number basically as charge. So the charge of the ion changes. And I'll tell you right now, redox reaction was one of the most confusing things I had to learn in chemistry. As basically is a lot of opposites that you have to memorize. Oxidation is loss of electrons or an increase in oxidation number. Reduction is a gain of electrons or a decrease in oxidation number. There is a nice mnemonic for remembering this. The reason why this was always confusing to me is you have to remember that when you increase electrons, your number is going to become more negative, or like if you have -1 charge and it goes to -2, you are gaining an electron. And because we're dealing with negative numbers, that's a decrease in oxidation number. You're going from -1 to -2, that number is smaller. Which, if you're not realizing that the fact there's a negative there, going from 1 to 2 is gaining or increasing a number, but going from -1 to -2 is the other way. And that's what's always made it confusing to me. An oxidizing agent is an electron acceptor. Species oxidizes another and it is itself reduced. A reducing agent is an electron donor. The species reduces another and is itself oxidized. Again, we have this opposite terminology in it. A reducing agent is oxidized. An oxidizing agent is reduced. An oxidizing agent will oxidize something else. Everyone good? Oil rig. This is the mnemonic you should memorize. Oil stands for oxidation is loss. Rig stands for reduction is gain. So if you're losing electrons, you're being oxidized. If you're gaining electrons, you're being reduced. And also, the fact that you're reducing something means gaining. Is backwards thinking, but it's in reference to oxidation number. It is you're reducing the oxidation number by gaining electrons. Another one is Leo the lion says grr. Leo stands for loss of electron, or lose electrons is oxidation. Grr stands for gain electrons is reduction. So those are two nice mnemonics. I always remembered oil rig. So oxidation cannot happen without reduction, and reduction cannot happen without oxidization. If you see something has been reduced, if you see some oxidation number, a charge has changed, there has to be another thing that also changed. So the oxidation number of an atom is the number of electrons lost or gained when it forms an ion. Oxidation numbers are written with the sign before the number, whereas ionic charge is written with the number written after the number. And I never, this is where I told you it's important to distinguish between it, but I said it didn't matter. I've been trying to do it throughout the year. So when you write the charge on the ion on the top right, the number of the plus or minus sign should come after. But if you're saying what is the charge or really what is the oxidation number, then you should put the number in front. I'm not going to take off for that because it's been used throughout, and I don't want to confuse y'all or make y'all change up how y'all been writing it. But that is the standard. And again, I usually say the charge are the same thing as oxidation number, when technically it's how many electrons are lost or gained. So let's do this example that is showed in that picture. We have zinc, which is solid, reacting with hydrochloric acid, making zinc chloride and hydrogen gas. So what is the charge on zinc? What is the oxidation number on zinc? Do not need to look at the periodic table. It's a compound or an element. Elements have no charges. So the oxidation number is 0. However, when it bonds ionically to the chlorine, well, we know the chlorine has a negative charge, and there's 2 of them. So that means the zinc, to balance out the 2 chlorines, would have to have a 2 plus charge, right? So the oxidation number for zinc is now plus 2. So it has gone from 0 oxidation number to plus 2. Does that make sense? So this means, is this oxidation or reduction? So oil rig. Rig stands for reduction, is gain of electrons. When you gain electrons, you become what? More negative. It's gone from 0 to plus 2. Oxidation is loss of electrons. It is lost 2 electrons to become plus 2. So zinc is reduction and undergoes reduction. So where is there oxidation? If something is being reduced, something else must be oxidized. What is being oxidized? So what is the charge on chlorine over here?
-2.
Chlorine is negative. So that doesn't matter. We basically have 2 HCl, but in both of them it still has a charge of negative. And over here we have that. So these haven't changed. hydrogen has a plus. And what about over here on H2? H2 is 2 hydrogen. One of them is it's basically one of them is being oxidized. One of them is changing state. So over here, let me illustrate this. So we have zinc plus HCl plus HCl, 2 HCl's, and we're making zinc chloride and hydrogen 2. This hydrogen is plus 1, so it has a +1 oxidation number. This one has H+, so its oxidation number is +1. Hydrogen 2 is, we know one of them is going to be H+, and one of them is going to be H-, right? Technically, this is covalent bonding, but we can treat it as ionic temporarily. So remember that in the carbon group, carbon can either be +4 or -4, right? Because to get 8 valence electrons, it can either add 4 electrons or remove 4 electrons, right? Hydrogen is in the same situation. It can either be +1 or -1. So if we treat this as an ionic, one of these ones can be H+, and one of them can be H-. So if we compare this one and this one, the charge is the same. The oxidation number is the same. So this one has a oxidation of +1. This one has a oxidation of -1. What this means is this one has gone from +1 to -1 by gaining 2 electrons. And I just realized you had me confused earlier when you said reduction. Oxidation. It has lost 2 electrons. I even said it. But still wrote it. Reduction. At least I think I did. So this hydrogen has gained 2 electrons to go from +1 to -1. So one of the hydrogen is being reduced. I can't even see what that is. That's all the oxidation numbers. Let's see if I can pull that up. It's really hard to see. So carbon can be +4 or -4. It's usually +4. There is a chance it could be +2. The half numbers are really weird to work with. Oxygen is normally -2, but there is sometimes some situations where it's not. That's just showing the common oxidation numbers. So the oxidation number of an uncombined atom is 0. I guess this is another way of looking at it. It's saying O2 you can treat as having an oxidation number of 0 because it's covalent. I always thought of it as one of them becoming, but it works out the same. So treating it as 2H plus, and over here they're treating it as having 0 because it's covalent, not ionic. That's going from 2 plus to 0, so that is a gain of electrons. The math works out the same though. I think I'll stick with the PowerPoint. The oxidation number of uncombined ion is equal to the number. Is equal to the charge of the ion. So Ca2 plus oxidation number is +2. Basically, the oxidation number and the charge are the same thing. The oxidation number of oxygen in compounds is -2. The oxidation number of hydrogen in compounds is +1. Basically, this just tells you the charge. Figure out the charges. 2. Group 1A becomes +1. Group 2A is +2. The oxidation number of more electronegative atom in a compound is the charge of the ion. So in silicon tetrachloride, chlorine is more electronegative, so chlorine has an oxidation of -1. So this is where oxidation number and charge differ. So silicon doesn't get a charge of +6. So for example, whenever I've been telling y'all how to figure out the charge of the ion, so like sulfate, I've been saying the charge of oxygen is -2. You multiply by 4, that's over here, you get -8. And you can treat the charge of this as being +6, giving this a net -2. It would be better to say the oxidation number of oxygen is -2. The oxidation number of sulfur is +6. Then you can convert the combined oxidation number into a charge. Because sulfur does not get a charge, but does have an oxidation number. So when you have a covalent compound, the more electro one will always get the negative number. So going back to like sulfur. Oxygen is more electronegative, so we're going to give it an oxidation number of -2. That means the other one is going to have a positive oxidation number to counteract it. The sum of the oxidation numbers in a neutral compound is 0. The sum of the oxidation numbers of the atoms in a polyatomic ion is equal to the charge of the ion. Nothing we've been doing differently. So oxidation number and charge are very similar concepts. There is a slight difference, but basically if you just treat it as charge, it should all work out to be the same. What is the oxidation number of chlorine in KClO3? So what are the oxidation numbers for everything in here? Oxygen is always -2. Group 1, calcium, will always get +1. So this is potassium chlorate. It's a compound. So what is the overall charge? 0. So the net charge is 0. That means whatever oxidation number chlorine is has to balance this out. So we have a +1 plus whatever chlorine is plus 3 times -2 has to equal 0. So that'd be +1 plus x plus -6 has to equal 0. +1 plus x, moving this over, is equal to 6. Moving the 1 over, x is equal to 5. So that means chlorine's oxidation number is +5. That makes sense? So for this one, sulfite, what is the oxidation number on sulfur? Well, again, we know the net charge is -2. So the sum of oxidation numbers has to equal -2. Oxygen is always -2. So we have x plus 3 times -2 has to equal -2. So x minus 6 is equal to -2. Add 6 to both sides. X is equal to +4. So that means sulfur has an oxidation number of +4. Make sense? And remember, I told you that for the 8 versions, when doing oxyions, you can treat the group number as being the oxidation number charge. So in the 8 version, to figure out the charge, you can get sulfur has an oxidation number equal to its group number. Even if you didn't know that, if you just knew that this is 2 negative, it's the same thing. So we have sulfur plus 4 times -2 has to equal -2. Sulfur plus -8 is equal to -2. Adding 8 to both sides, we see sulfur is equal to +6, which is its group number. Not only works for its different exceptions for the halogens and group 7 and 8. Alright, I'm looking at this, and the way I first said it is treating hydrogen is probably wrong. And it works out the same way as how I originally thought of it and did it because the math works out. But this is so much simpler, and we'll go with it. So, looking at these 2 questions that we just did, so the oxidation numbers must add up to 0 because it's a compound. The compound has no charge. The oxidation number of oxygen is always going to be -2. Group 1A always has +1 as an oxidation number, so you just figure out what chlorine is. So looking at our rules are oxygen is always -2, hydrogen is always +1, 1A and 2A. 1A is always plus 1, 2A is plus 2. Anything left over, basically, you're going to have to figure out and calculate. So, if you turn it into the net ionic equation, it makes this very obvious what is being reduced and what is not. Here, there are saying treat hydrogen H2 as having ionic or having a covalent or oxidation number 0. I think we'll stick with that way. In which case, here we have a 2H plus going to H2, which is 0. So we have 2 hydrogens with a plus charge going to H2 with a 0. I always liked breaking that up, though. It's weird that this PowerPoint doesn't do it. And it works out the same. The math does. But we'll continue this tomorrow with more examples.